Good afternoon, everyone. Welcome to my talk on Rayleigh-Bernard convection, the boundary layers of Rayleigh-Bernard convection at very high Rayleigh numbers. So, as Martis had mentioned, I'm a postdoctoral researcher working with Professor Jörg Schumacher's lab in TU Ilmenau. And this work has been done in collaboration with Martis, Janet Scheel, K.R. Srinivas, and K.R. Srinivasan. Prafula is a fellow postdoc from the lab. So before I start the talk, I'll give a brief outline of what I'm going to be talking about today. So I'll start with the introduction of with a brief introduction on the governing equations and the NIC-RS solver that we are using to run our simulations. And then briefly, we'll go through the temperature profiles and velocity profiles that we have gotten from for the thermal convection from our DNS. And then we'll look into the interesting part, which is basically the structure of boundary layer flow, which is the focus of the talk. And then a self-similarity of the boundary layer flow. And finally, we will look at how massless tracers disperse in thermal convection. So to start off with, why do thermal convection? Why do we focus on that? So we see thermal convection in a wide variety of natural phenomena and in engineering systems. For instance, automotive cooling, cooling of electronics, and so on. So, for instance, what we see, what's there on the right-hand side is the surface of the sun, and we can see turbulent convection happening on the surface of the sun. Each of these granules that you see is roughly the size of Germany. So that's the kind of scale that we are looking at over here. And so when it comes to convection in such systems like the sun, atmospheric phenomena, and so on, one important feature of the system is that it is not confined in the sides. It's unbounded. It's like it's thermal convection happening between a pair of parallel plates, as we see over here. As we see in as we see in this case. So in order to understand. And on the left is a result of the simulations that we have run and I'll be talking in detail about these in the upcoming slides. So moving on, what the governing equations that we solve, these are well known to all of us. These are the Navier-Stokes equation with energy and continuity, and the three main parameters that we tweak in our simulations are Rayleigh number, and Prandtl number and aspect ratio. Prandtl number is kept constant at 0.7, aspect ratio is 4, and I'll discuss in detail about what the aspect ratio is next. So we simulate the convection in a rectangular domain of height h and L 4 times h, and that's where the aspect ratio comes up. We use periodic boundary conditions in the along the horizontal directions and no slip boundary conditions in the vertical. And roughly for the lowest Rayleigh number, this is how the flow would look like, with hot fluid rising from the top and cold fluid falling from, hot fluid rising from the bottom and cold fluid falling from the top. And this is at the lowest Rayleigh number. So things get interesting as we increase the Rayleigh number. This is for 10 power 5, and we are exploring up to 10 power 12. So before discussing the results, I would like to briefly talk about the code that we are using and the infrastructure that we have used. We have used NIC-RS GPU accelerated spectral element code for all our simulations, and we have run our simulations on the GWS booster cluster using as many as we have run full machines runs, in which we have used up to 3,300 NVIDIA 800 GPUs for our simulations. And this is the full list of simulations that we have run. At the highest end, we are going up to nearly 47 billion points in the domain. So these are among the highest resolution simulations of Rayleigh-Bernard convection that have been run so far. And despite the high resolution, in order to get reliable statistics of the flow, we normally need to run the simulation for a long period of time. So we need to run it. So we have run for a minimum of 25 free fall units of time to ensure that we get reliable statistics from all our simulations. So, and one more thing that I would like to briefly talk about is how NIC-RS scales for Rayleigh-Bernard convection. So these are some of the times taken by NECARIS for computing 1,000 time steps. So in seconds, we have plotted the time taken by NECARIS for computing 1,000 time steps for Rayleigh 10 power 9, 10, 11, and 12. So these are the highest Rayleigh cases. And we can see that the scaling is the NECARIS scales very well as long as you have a certain minimum number of points per GPU. So for instance, if we look at 10 power 9 and 10 power 12, which are this red and green curves, after a certain point, the scaling is no longer ideal. And that is when the number of points per GPU falls below roughly 4 million points per GPU, at which point the scaling is not very ideal. As long as we have more than 4 million points per GPU, NECARIS scales exceptionally well. And we can see that very well in 10 power 11 and 10 power 12 especially. And so now we look at some temperature and velocity profiles from the simulations. So, and before that, the global quantities that we look at are Reynolds number and Nusselt number. So Nusselt number is a measure of how well heat is transported by convection from the across the plates as we increase the like for a given Rayleigh number. And Reynolds number is a measure of how turbulent the flow is, how well momentum is being transported by convection between the two plates. So these are two global quantities of interest for thermal convection community. And we look at the scaling of these two quantities. On the left, we look at Nusselt number scaling. So it is a well-known result in thermal convection that Nusselt number, first of all, with Rayleigh number, Nusselt number will also increase. But however, there's a specific law by which Nusselt number increases with Rayleigh number, and that is Ra power 1/3. So that's why we have plotted compensated plots where we have divided Nusselt by Rayleigh power approximately 1/3. And we can see that at high Rayleigh numbers, they all become flat, which indicates that it's following the classical scaling law of Ra power 1/3. Though there are some groups which have claimed that the Nusselt number will scale at a factor higher than 1/3 for certain large Rayleigh numbers. At least in our simulation so far, we have not been able to see that higher than 1/3 scaling, which is also called ultimate regime. So moving on to Reynolds number. So one thing that we can see from Nusselt number is that we have plotted both Nusselt number and Reynolds number against two existing cases from literature. One is using a thin cylinder. The other is using an aspect ratio 1 cylinder. And the thin cylinder results are from Iyer et al. And the aspect ratio 1 cylinder is by Shiel et al. And when we look at the Nusselt number scaling, for all three cases, they all collapse well in one line. However, for Reynolds number, we see that the variation is much more different. They don't match, they don't coincide on one top of the other like how we see in Nusselt number. So what this means is that the Reynolds number is very much dependent on the geometry. Furthermore, one more thing to note is that the geometry that we use, this aspect ratio 4 box, it's periodic, it's open. But these two geometries are actually closed geometries. So the shape of the geometry and the boundary conditions on the sides have a significant impact on how the flow organizes itself within the cell. And that's reflected clearly in the Reynolds number scaling. And when we look at the temperature profiles, well, there's nothing surprising or out of the ordinary. As Rayleigh number increases, the thermal boundary layer becomes thinner, which is expected. So we can see that from the mean temperature profile. We can see that for the highest Rayleigh number, the thermal boundary layer is hardly visible. It's very, very narrow. But for the highest for the lowest Rayleigh number of 10 power 5, the boundary layer is almost going up to the middle of the domain. Well, actually, it's not going up till there. And we can also look at the boundary layer thickness by looking at the TRMS profiles, which again shows how the boundary layer thickness decreases as the Rayleigh number increases. And in here, we have also tabulated the variation boundary layer thickness. And one thing to note is that for the highest Rayleigh number of 10 power 12, the boundary layer is of the order 10 power -4. And this shows that for very high Rayleigh number, how much of resolution we need in the vertical direction. Because in order to resolve the boundary layer properly, we need to have a minimum number of points within the boundary layer. Otherwise, we won't be able to capture the dynamics of the boundary layer, which is what we are focusing over here. So even for the highest Rayleigh number of 10 power 12, we have around 10 points in the boundary layer. So which shows that our simulations are well resolved. So, moving on to another interesting aspect of Necaris basically is that we ran the highest Rayleigh number. We ran 10 power 10 and 10 power 11 with different vertical resolutions. Again, as we mentioned, vertical resolution is important. So we have varied the number of points in the boundary layer anywhere between 11 to 16 for both these cases. And we see that the TRMS profiles, they all collapse very well, irrespective of how coarse the boundary layer is. So basically, we need at least 10 points in the boundary layer. And there are some research groups there are some research results, like simulation results, which say that we need around 15 points in the boundary layer. But one thing to note in these cases is that it depends on the numerical method that you're using. So we are using spectral element method, and it has been shown that for spectral element method, even with 10 points in the boundary layer and even with a coarser resolution, we can get reasonably good results. But when it comes to finite difference methods, this might not be sufficient. For finite difference methods, we might need more points in the domain to resolve all the features of the flow. So, what we intend to show over here is that the boundary layer resolutions that we have used, we have been more cautious with it. We have used up to 16 points just to ensure that, yeah, like there is no question, there's no doubt that the results are reliable. And then we look at the velocity profiles in the boundary layer. So there are two ways that we have looked at the velocity profile. So when we look at the plate, at the bottom plate, we can look at the velocity parallel to the plate, which is taken from UX and UY, and that is what we call UH-RMS. And then we can take all three components, which is URMS. And we look at the boundary layer thickness based on both these quantities, and we can see that the UH-RMS boundary layer thicknesses are smaller than the URMS boundary layer thicknesses. And this has an important implication, which we will discuss in the coming slides. So it shows how the boundary layer thicknesses are are dependent on the geometry. So that's what I'm getting to. I'll show that in the upcoming slides. And another interesting comparison is the boundary layer thickness based on TRMS and URMS. If we see, the boundary layer thicknesses are very different. For instance, if we look at it for temperature-based boundary layer and velocity-based boundary layer, the velocity-based boundary layer is much thicker, of the order sometimes more than 10 times thicker as compared to the delta TRMS. And note that we are running our simulations at approximately Prandtl number of the order 1. So for Prandtl number of the order 1, we normally expect both the boundary layers to have similar comparable thicknesses, but that's not what we see over here. So again, why is there this difference in the boundary layer thickness at Prandtl number unity is another interesting question that we'll look at in the upcoming slides. And before moving on to investigating the boundary layer profiles, before moving on with our results, we also look at whether the aspect ratio that we have chosen is sufficient for our studies. So we have used aspect ratio 4, but in some scenarios, it may be necessary that we need larger aspect ratio to completely avoid the effect of the side walls of the domain. So in order to ensure that aspect ratio 4 is sufficient, we ran for Rayleigh 10.9, we ran our simulations for gamma 2, 4, and 8. And we can see that gamma 2 is clearly not sufficient, at least when it comes to the impact on velocity boundary layer. Velocity boundary layer, as we have already seen in the Reynolds number scaling, the velocity boundary layer is more significantly affected by the domain geometry, right? So that's why we can clearly see that the velocity boundary layer is different for gamma 2. But for gamma 4 and 8, they're all comparable. So this shows that gamma 4 is a good compromise. For larger gamma, we need larger number of points, and the requirement, the computational resource requirement also grows much higher for larger gamma. So we stick with gamma 4 for all our simulations. So one interesting aspect of the boundary layer in RBC is, can a Blasius type boundary layer fit the velocity profile of Rayleigh-Bénard convection? This is another question that's been discussed in the community. So the thing is, The glasses boundary layer profile is what we normally see for flow over a flat plate. As we see, there's a U infinity and there's a boundary layer developing over the flat plate due to the flow across it. So the Blas's boundary layer profile can be quickly derived from the Navier-Stokes equation by reducing it to the 2D form of it and applying some scaling arguments to remove extra terms. And then using a non-dimensional stream function in terms of a variable f, we can basically derive this ODE, which when we solve using shooting method, we will get the following profile. So this is the well-known Blas's profile that we see in flow over a flat plate. So now we check whether the flow over the bottom plate or flow over either of the top and bottom plates fits this profile for RBC. So when we look at the flow over the full domain for RBC, it's random. And this is because it's basically flow between two parallel plates purely driven by convection with periodic boundary conditions. So the flow is basically random in the bulk of the domain. But if we look if we look close to the bottom plate, we can see, okay, so there is a variation that may look like Blas's profile. And then after we normalize all these profiles and we fit them with the Blas's profile that we have seen over here. And we fit them using two constants, U infinity and delta infinity. These are the two constants by which we fit the profiles to the Blas's type boundary layer. And when we look at how these constants vary, they are varying very randomly. So many of the theories in understanding the boundary layer of RBC, which develop from assuming a Blas's type boundary layer, may not work in the case of RBC, at least in the context of unconfined RBC as we are looking at over here. So that's the main takeaway from this. And moving on to the structure of the boundary layer flow. So this is a simulation of the boundary layer flow. So this is taken at a plane of z equals to delta t, which is at the limit of the thermal boundary layer. And what we see are the temperature contours over here. And this animation is made using an in situ visualization tool called Ascent, about which Jens will be talking in greater detail in the next session. So what we see is how turbulent the flow in the boundary layer is at such high Rayleigh numbers. And we also look at the velocity streamlines at 10 power 11. And one thing that we need to notice in this case is that there isn't a coherent flow that spans the entire surface as we see. So we see one patch of coherent region over here, another patch of coherent region over there. But in between, there are these regions of plume upwelling, right? So this is probably why we cannot fit a Blas's type boundary layer to understand the dynamics of the boundary, Blas's type profile to understand the dynamics of boundary layer in RBC, because there isn't a coherent flow that spans the entire plate like how we would see in, say, a flow over a flat plate, right? So in order to understand that further, we need to, first of all, split the flow into coherent regions and incoherent regions, these plume upwelling and shear dominated regions. Just to compare, this is gamma 4 simulations that we have run, right, at 10 power 10. If we look at gamma 1 simulations in a closed cylinder, which we had compared earlier in our Reynolds number and Nusselt number scaling, we can see that there is a definite coherent flow aligned along one direction, along this arrow. But we don't see that such a similar situation in planar RBC. So that's why I had said earlier that due to this lack of a coherent flow, when we average over the entire plate, it's bound to be random. That's what we had seen earlier. So now so what if we split the flow into coherent and decoherent regions? So we do that by splitting up the domain into 100 cross 100 cells. And in each cell, we compute a URMS. And then we check whether the URMS within each cell is greater than or lesser than the URMS computed over the entire plane. And based on that, if the URMS computed over a single cell is less than the global URMS at this plane, we call that decoherent flow, which is marked in these black regions. And if it is greater than the global URMS at that plane, it's shear dominated coherent flow. Based on this, we split the flow into coherent and decoherent regions. Now we can look at the profiles in these two regions separately. But one interesting thing to note is that the ratio of coherent and decoherent regions that we see is constant for all Rayleigh numbers. As for from 10 power 5 to 10 power 11, the ratio is of the order 40% of the plate. So shear dominated regions occupy 40% of the plate, and plume upwelling regions occupy 60% of the plate. So based on that, we split the flow, and we now observe how the coherent and the shear dominated and plume dominated regions affect the flow in the bulk. So in order to, so once we split up so this is for gamma, for RA equals to 10 power 10. Again, we look at a height of delta T of the delta T. We look at the velocity profile, the velocity field, and we split it up into shear dominated and plume dominated regions. And furthermore, if we look at a height at a plane slightly above, at least 25 times the thermal boundary layer thickness, we can see that the plume dominated regions that you see over here coincide well with the plumes that are rising from the plate. This is the temperature contours, and these red regions indicate the regions from where plumes are rising from the plate. The blue regions indicate where the flow is impinging on the plate. So based on that, we can see that these plume-dominated regions are corresponding with the regions where the temperature is high in the bulk. And similarly, for the top plate also, the plume-dominated or the decoherent regions correspond with the regions where the temperature is, where the plumes are falling down into the bulk. So it establishes a correlation between the plume-dominated region and the temperature profiles within the bulk. And another thing that we looked at is whether when we split up the flow based on URMS, if there's a factor by which we should split up. Like we have decided that decoherent is any cell with velocity which is less than the URMS. But what if we take a factor? And the area fraction will definitely be sensitive to the factor. So based on that, we chose 3 factors, 0.5. And so we chose 2 factors apart from 1, 0.5 and 2. And we can clearly see that if we use a very high threshold, the entire plate will become plume dominated. If we use a very low threshold, the entire plate will become shear dominated, which is understandable. So using URMS, using a unity factor is ideal for splitting the flow in the plate into shear dominated and plume dominated regions. But despite that, the area fraction still remains constant. Even if we change the factor, the area fraction is constant for all Rayleigh numbers, going from 10 power 5 to 10 power 11. So after splitting the flow over the plate into plume-dominated and shear-dominated regions, if we now condition the velocity profiles on the plate on these 2 regions, if we look at the velocity within the shear-dominated regions, which is what, earlier we had seen that the velocity boundary layer thickness is very high, right? So this is the original URMS boundary layer thickness for 3 Rayleigh numbers that we had chosen for our analysis over here. But if we now just look at the coherent regions and again look at the velocity profiles within only the shear dominated region, then the velocity profiles become thinner. So, and now another interesting thing is that it is comparable to what we see in the closed cylinder. So where we saw that there is a coherent flow spanning the entire bottom plate, if we look at only the coherent regions, then the velocity boundary layers are comparable for both the cases. So again, the crux of the argument is that we need to look at the flow in the RBC as a mixture of plume-dominated regions and shear-dominated regions and treat it accordingly, not as one coherent shear-dominated region. Now, self-similarity of the boundary layer flow is another interesting aspect of Rayleigh convection. So in here, there are simulations of, there are animations of thermal convection at Rayleigh 10 power 5, which you have seen earlier, and 10 power 9. Clearly, the 10 power 9 simulation, it's much more frenetic. There's a lot more activity going on as compared to 10 power 5. Despite that, there exists interesting self-similarity in the flow, both spatially and temporally across these 2 Rayleigh numbers and higher. So we look at what is the self-similarity in RBC for by both spatial and temporal in the upcoming slides. So before doing that, we look at the shear field on the bottom plate and we decompose it into, we compute the eigen values of the shear field, and then we decompose the flow into nodes, saddles, and foci. And then, for instance, if we look at for 10 power 5, if we look at how the flow is organized on the boundary layer, we can see that there are nodes where the flow is either rising from the is where the flow is impinging on the plate, and then there are these narrow saddle points from where the plumes are rising from the plate. And these node saddle node triplets are basically indicative of a plume that is rising from the plate. So we use this decomposition of the flow of the velocity field on the plate to get an idea of the structure of how the plumes are organized on the plate. And then we now we base initially just for an preliminary picture, we look at how the flow varies for different Rayleigh numbers, how the number of nodes, saddles, and foci vary with the Rayleigh number. So when we look at that, as the Rayleigh number increases, the number of nodes and saddles and foci, of course, they increase greatly as the Rayleigh number increases. Another interesting thing to note is that the distribution of nodes, saddles, and foci is not uniform. There are some regions where there are no critical points at all, and then there are some regions where all the critical points are clustered together. Right. So, for instance, we can also see that the critical points are clustering together in certain structures, which are known as the turbulence superstructures of thermal convection. So then, after looking at how the critical points are distributed across the plate, we investigated it further to see how, if there's a connection in how the critical points are distributed for different Rayleigh numbers. So on the left, we have the temperature field and the critical point distribution for Rayleigh 10 power 6. And on the right, we have the same for 10 power 11. But if we now take a small cell in the center of the box for 10 power 11 and we zoom into it, then if we look at how the critical points and the temperature field look, it's very similar to what we see at 10 power 6. So there at least on a qualitative sense, we see that there is a self-similarity of the flow. So though they are separated by several decades of Rayleigh number, we see that there is a similarity of the flow at the smallest scales. And then another thing to note is that this similarity is not uniform over the plate. There is an intermittency to the turbulence on the plate, right? So if we look at the same cell and if we compare it, how the flow within that same region varies as compared to the flow over the entire domain for Rayleigh 10 power 6, it's not all the same similar to what we see in 10 power 6. There are sometimes where you don't see any critical points, sometimes when we see that they are very similar. So it's for a specific snapshot that we had seen that self-similarity. But if we now to try to quantify this self-similarity, we first look at all the temperature contours for all Rayleigh numbers ranging from 10 power 5 to 10 power 6. This is how the contours become finer as we increase the Rayleigh number. But now if we take the 10 power 12 case and look into a small square within that and zoom into it, we can see, first of all, we use a magnification factor of 2 and use that such that if the original cell is of size L, the next cell is of size L by 2, and so on. So we see that there's a comparison between 10 power 11 and that and the bottom and the zoomed in section of 10 power 12 in the bottom row. And proceeding further all the way, if we zoom in successively to each cell one by one until we reach 7 times, we zoom into a section of 10 power 12, we can see that there is still a similarity of the structures between 10 power 5 and this flow of 10 power 12. And this zooming factor that we have chosen over here of 2, this is more sensitive. We have actually looked at how to estimate this correctly, and there is actually the actual factor is close to 2, but it depends on the plume width. So we are now looking at how to estimate the zooming factor correctly using the plume width. So we also calculate the interplume spacing lambda p, and based on that, we are trying to estimate the exact zooming factor such that we can quantify the spatial self-similarity of RBC properly. Finally, there also exists a temporal self-similarity. So we place a probe in the boundary layer, at the edge of the boundary layer, and measure the velocity field, velocity at that point. And if we look at how the velocity varies for different Rayleigh numbers, we can see, okay, for low Rayleigh numbers, the variation is very slow, but for higher Rayleigh numbers, there's a much more high frequency variation of the velocity field. But if we now compute a self-similarity parameter for the time, which is tau, based on the plume spacing lambda p and the URMS. And then if we use that to scale out the time, scale out the variation in time, then we see that there is, first of all, it is comparable, but more importantly, if we look at the spectra of the time series of velocity field, if we look at the original spectra, as we see, as the Rayleigh number increases, the frequency also increases. But when we take the spectra of the time-scaled velocity field, we see that all the spectra collapse one on top of the other for all the Rayleigh numbers, roughly. So again, this shows that there is a temporal self-similarity in the flow of in the boundary layer flow of RBC. So final section of my talk is on Lagrangian tracers. So what we do over here is that we take a small section. So we take a small section of two cross two. So the domain is spanning from -2 to +2 for the gamma 4 case. So we take the middle quadrant and we release approximately more than 1 million massless tracers of Stokes number 0, and at a height of z equals to delta t by 4, so that all the particles are initially well within the boundary layer. And then we implemented the reflection such that if any particles goes towards the wall, it will be sent back into it. And if any particle tries to move through the left or right, it will be sent from the other end through periodic boundary conditions, such that the particle count is perfectly preserved. And we perform these simulations for Rayleigh numbers ranging from 10 power 5 to 10 power 11. So basically, so initially when we look at for 10 power 8, we can see how the particles rise up with the plumes. And the reason why we do this is so that we can look at, we are refining how we compute the plume width. So to do that, we are looking at how the particles cluster. The particles tend to rise up with the plumes. So the regions where it's shear dominated, the particles will be driven out of there and they will all collect at the plumes. And based on the interparticle distance, we can get an idea of where the plumes are. Though it's not very clear in this video where we are looking at it from the sides, if we look from the top, we can see how the particles are aligned with the plumes. So we can see all the shear dominated regions become sparse and the plumes are where the particles are coming together. And these are for 3 Rayleigh numbers from 10 power 5, 7, and 9. And one thing to note is that for it looks like the animation is moving slowly for higher Rayleigh numbers, all 3 simulations cover exactly 5 free fall times. It's just that we have a finer sampling rate for the higher Rayleigh numbers because we take the data at every 5 time steps or 10 time steps, so that we get very well resolved data about how the particles move in the domain. And finally, just before moving on, one more thing that these are some of the preliminary cases which we looked at. So again, for 10 power 6 all the way up to 10 power 11. And we can see for the highest Rayleigh number, the particles just go into a kind of slight orange mist. So this shows how well the turbulence is dispersing the particles up throughout the bulk of the domain for high Rayleigh numbers. And another thing that is interesting to note is for the low Rayleigh numbers of 10 power 6, we can see that even after 10 free fall times, the particles are still, you can still see, okay. That's odd. Okay, the animation just glitched out. Well, okay. So the thing is, there was this small discussion that I had with Martis. He had asked, do you think the flow at Rayleigh 10 power 6 is turbulent enough? So one thing is, we can see that at high Rayleigh numbers, the particles are clearly dispersed very well by turbulence. But for low Rayleigh numbers, we can still see the particles clumped together and moving slowly. And the interesting thing is this shows how turbulent is kind of an emergent phenomenon, right? Because we had seen earlier that this flow is self-similar to this flow. 10 power 6 and 10 power 11, there's a self-similarity. If we look at a small section of 10 power 11, it's basically the same kind of dynamics. But yet, as we go up the scales, the turbulence manifests itself as like a much more faster dispersion of particles. So that's how we can see, this is just an idea of how turbulence is an emergent phenomenon that comes out of the like a number of like multi-scale phenomenon. Because it's a multi-scale phenomenon, as we go up the scales, it becomes more the mixing ability of the fluid increases greatly. So before winding up, there's one more thing that we looked at is what is the performance penalty of including particles in our simulations. So with tracers and without tracers, there isn't a huge performance penalty when it comes to NECARs. The penalty is roughly of the order. So with tracers, it takes 0.193 seconds per time step. Without tracers, it's 0.186. So the penalty is only 3.5%, which shows that the particle dispersion code is implemented quite well optimized in NECARs. But one thing to note is that the particles that we have used are massless, so we don't take the velocity degrees of freedom, and we don't compute the acceleration. We just track this position with respect to time. So maybe for particles with mass, there might be a higher penalty, but at least in this case, the penalty is not very severe. So in conclusion, what we see is that the flow of the boundary layer flow of RBC is organized into shear dominated and plume dominated regions. And the plume dominated regions occupy roughly 60% of the plate, and shear dominated regions occupy roughly 40% of the area of the plate. All the critical points tend to cluster around the plume dominated regions. And the boundary layer thicknesses are different in these two regions too. And finally, the conclusions apart from that is like we find that the classical 1/3 scaling holds for all the Rayleigh numbers up to 10 power 11 in our cases. There is a difference in how the momentum transfer is scales and it depends a lot on the boundary conditions and the geometry of the domain. And finally, gamma equals to 4 is sufficient to capture all the horizontal homogeneity that we have reported on. Massless tracers tend to cluster in plume upwelling regions, and this allows us to measure plume widths. And the results that have presented here was recently accepted for publication in JFM, and this is a link to the paper. Thank you.